And we're rolling again. Okay, so I want you guys to grab a partner. Everybody, point to your partner right now. Okay, I see a bunch of you pointing at yourself. That's fine by me. Okay, I want you to try to figure this out. Take a minute, see if you can draw shapes. I want them still to be rectangles. I want you to draw rectangles and try to shrink this shape, or shrink those gaps. I'll give you about 3 minutes to try to come up with a method that will shrink those error bar, or these error gaps.
What's the height?
Let's say that goes up to 2. Let's make it a semicircle. Now we all know how to find the area of a semicircle, but I want you to try to approximate it using rectangles. What can we do to shrink it? Okay. I'm going to take attendance while we're doing this. Okay, attendance. Where? Okay, attendance. Diana. Tierra. Gamble's out.
Yeah.
John.
Sure.
Kelsey.
Yeah, careful.
Tamara. Tamara. Jonah.
Here.
B.
Here.
Chantel is out. Is out. Kamala.
Here.
Travar. Dina. No Dina today. Michael. Insular. Note that I'm not asking you to actually do any math here. I'm not actually asking you to find the area of these rectangles. I just want you to try to see if you can figure out something that can shrink these errors.
Could you do like the 2 middle, like make this one right, make this one left?
Okay, I did.
Because it's gonna go that way, right?
You sure did. That is how we will make it closer to the approximation.
Approximation method, the last 2. Yeah.
Hey, is this gonna lead us back to limits as we get closer and closer to the answer?
Limits are definitely going to be involved at some point.
You can probably do either both and then do I don't know, what I'm saying is just use both.
Okay. So, what can we do to shrink these error bars? What can we do to make our rectangles fit the circle more closely?
Use all the methods.
Use all of them. Well, let's just stick with rectangles for right now. And make it more illustrative.
Don't go over as much.
Don't go over as much. Okay. How would I maybe...
Average them all.
Averaging them all would be the trapezoidal method. That would be us, going from here to here,
Yeah.
there to there, there to there, there to there. And it's a pretty good method.
Might as well.
But using the same right-handed method, what can I do to shrink these error bars? That is averaging it again. Okay, John, what can we do to
Use smaller rectangles. Go right by.
we can use smaller
0.001
rectangles.
instead of 1.
Okay, let's make it a little easier. What if I ask this question, every year, see if people can figure it out. Sometimes they do, sometimes they don't. What if we make smaller rectangles? instead of going left by 1, how far should we go over? 0.1? That'd be pretty small. That'd be hard to draw.
0.01.
Let's go left by a half. That should make it clear enough what's going on. So let's go left. Start on the right side. Go up until I hit it right there. Then go left. Let's see. 1, 2, 3, 4. And go left by a half. Now go up until I hit it. Now how far am I going left? Go up until I hit the bar. Go left. Oh, but go left by half and down. Ah. Oh, I missed the first rectangle. Okay. 1, 2, 3, 4. Go up until I hit the circle. Go left by half and down. Go up until I hit the circle. Left by half and down. Up until I hit the circle. Left by half and down. Up until I hit the circle. Left by half. Down, up, left, down. Okay. So take a look at our gaps now.
There's more of them.
There are more gaps. But are the gaps anywhere near as big as they were over here?
No.
No, I mean, we had huge gaps here and there.
Huge.
So what's going to happen if we make it even smaller?
It'll be a lot more. Smaller.
It's going to be a lot harder to draw, for one thing.
Become infinitely small.
That is our ultimate goal. We won't get there today, though. Because that's going to require some actual, like, math and proofs and stuff. Gross. Okay, well, let's make them even smaller. How small should I go? 0.25. Let's have it again. Okay. So 1. Let's see. So 1, 2, 3, 4. So we have our halves. We have our wholes. But now we also have quarters. Oh dear. This is going to be a lot of rectangles. Well, up until I hit the line and go left. Hit the line and go left. Okay. So what's happened to our gaps? Now our gaps are getting pretty tiny. You can see that we have the biggest gaps over here on the end where our circle gets really steep, but even those are shrinking and shrinking.
Another one.
I think that's enough drawing of rectangles for me. But so if we want to get the closest approximation we can, how big do our triangles need to be?
Skinny.
Really, really skinny.
Rectangle.
Or our rectangle, yes, you're right.
Triangle.
Okay. So this distance here, the width of each rectangle, we're going to give a special name. We're going to call it delta x. So for this triangle, so for this approximation over here, how big is our delta x? How wide are our rectangles? Okay, how wide are them here? A half? What's our delta x over here?
25.
Our delta x here is 0.25. So how tall are each of the rectangles? Well, it varies, right? So we'll need some kind of variable. What variable do we use to tell us the height of something that's been graphed? Y. Okay. Okay, so if I want to find the area of our approximation, what are we going to do with all of these rectangles? We're going to add them together, but before we add them, what are we going to find for each one? We're going to find the area. So, how wide is each rectangle?
1.
For this one, it's 1, but in general, it's delta x. Now, how tall is each rectangle? Do we know exactly again? No, but we can use the variable y. So what's the area of each one?
Y times delta x.
Y times delta x. So then we got to add them all together. So this gives us a formula. What's the formula? What's the notation that we use for adding up lots of things? What's the symbol looks like? That means sum.
Like,
It's kind of like an E. What is it?
I don't know.
Do you know what it's actually called?
No.
So what does it look like? Help me out. Help me draw it.
Looks like an E.
Looks like an E, like this.
Looks like a W sideways.
Kind of like that.
An advanced E. Like,
Yeah. What's this symbol called? Do you guys know?
It's the sum sign.
It is the sum sign, and its name starts with S.
Cephalon.
Cephalon. That sounds cool, but no.
Some.
Epsilon.
This is sigma.
Oh,
Oh.
I know that.
So our formula then. Have you guys seen much sum notation?
It's spreadsheet.
Do you need it? Will you need us to do a review of this stuff, maybe?
Why?
Yeah, we can do. We'll might have to do a review of this stuff. We'll probably take a look at it tomorrow. But so our area is going to be the length of each one, or the height, which we know is y, times our delta x. We'll go ahead and say A approximately. Let's say A is approximately the sum of our y's times our delta x's. Do you remember what goes on top of these things? When
A.
On top, that's just is the number of rectangles we have. No, we don't have our number of rectangles will vary. Sum notation, the number on top is how many terms there are.
What's that?
And on the bottom, oh, the number on top?
No, whole formula.
Okay, I'll get there in a minute. And on bottom is our index. This is just where we're starting from. If we're doing a right-handed one, which means that we're starting at 1. Okay, equals 1. We have this thing right here. This is the formula for a Riemann sum. Yeah, named after the great mathematician Riemann, whose first name I don't remember. But
But he's so great.
he was so great, I assume. I don't know, I never hung out with him. Georg Friedrich Bernhard Riemann.
Yes.
God, that's quite the
Georg?
Georg. It's like George with no E at the end. Okay, so that's the formula for what we just been doing, which are Riemann sums. Okay, fair enough?
Yes.
Okay. Okay. I guess we have been going at it for about an hour and 15 minutes. Yeah, let's go ahead and take a 5-minute break. I'll go ahead and pause this thing. Okay.
Is that your name?